Hey, welcome back to part 2 of the four kinematics equation series. Alright, so now we have an idea of what the symbols mean when we see these equations. Some misconceptions, some language support. All of this is just build up right now, and you might be thinking, come on, let's just get to the actual stuff here. Okay, let's get to the actual stuff. So here, your big four awesome kinematics equations. Don't they look fantastic? Okay, it's like I'm trying to sell it at a grocery store. So what I'm going to do is I'm just going to go through each one very briefly. I mean, really, to be more familiar with this, the more you use it, the more you be familiar with it. I'm going to be talking about some a little bit of where it comes from, and but what I do want to do is I want to show you how it can be derived. And how is it derived from some of the other key basic equations that we already use. That, however, I don't require you to be able to do and to repeat or to show me. Mostly it's for your own interest and just to show you how cool and interesting how everything's connected. But that I won't require you to do. So this is how I will frame this next part. What I'm going to do is going to quickly go over each of these equations, and I'm going to talk about the key things I do want you to know. And after I talk about each of these, I will do my derivations for these equations. And that part of the video, you can fast forward, you can not watch it at all and just skip to the end and just look at what I wrote down. All of that is up to you, but I do want to quickly make sure you do watch this next little piece, okay? This first equation, let's jump in. The first one, we have the final velocity, initial velocity, acceleration time. And what you will see is that it actually comes from the basic definition of what acceleration is. And I did say I wasn't going to do any derivations, but I just want to quickly show you how you can go from here to there. It's very simple, it's very quick. In fact, if you want to try yourself, you can pause this video, see if you can rearrange this equation for it to look like this. But I do want to show you that this equation is essentially the definition of acceleration. So let's write this down. You have A equals to V minus U over T. The first things first, I'm going to move T to the other side of the equation. Getting rid of that. And then I am going to rewrite this. I have A T equals to final velocity minus initial velocity. I am almost there. I just need to move initial velocity to the other side now. And that's what I'll do by adding it using the opposite sign as what I have on this side. Minus and positives cancel out, which leaves me with U plus AT equals to final velocity. There we go. Rearranging it, this is what I have. I lied. I was going to show you derivations, but I really wanted to do this quickly just to show you it's the basic definition of acceleration. The next one we have is this one that we have. We have displacement, final velocity, initial velocity, time, and over 2. So let's give you a little idea what this is really talking about. We know S is your displacement, and I'm just going to put here total displacement. I mean, it's just the change in position, essentially. I wrote here, this is equal to average velocity times t. So what does this one all mean? And one thing that you will notice is t here that matches with that t. You have the sum of the final initial velocity divided by 2. So really, I could rewrite this as v plus u, okay, divided by 2, and all of that times time. Okay, that can be rewritten like that. It's something that you can do. Now, one big thing about this equation, and we've talked about this before, is it assumes that the acceleration is constant, and that is very important. If that's not the case, you can't take the average velocity of the final and the initial to give you your average velocity. It's just like you're trying to average out two of your tests. If they're weighed the same, then you can do it. You can add them together and divide that by 2. When you have constant acceleration, your velocity is constantly increasing, in which the middle of your, I'm going to say graph, in the middle of your, in the process, is your average, okay? But otherwise, you can't assume that. So what this equation really is you have the average velocity of your entire trip multiplied by the time to give you your displacement. Just like how displacement is your average velocity times time. Okay, isn't that cool? So it all comes from these basic assumptions. There's a lot of problems that people face with using this equation, so we will talk about this one when we get to those problems. Now, the last two, I'm not going to talk about their derivations, but they are pretty much variations on a common theme. We have displacement, initial velocity, time. Now we start to see acceleration, and here you have a time squared. Okay, so it's sometimes you might use this one. The last one, oh, sorry, and this, if you're curious, it is derived from the, it is in fact derived from the first two equations that we just talked about. Same thing with the last equation here. We have final velocity squared, initial velocity squared plus 2as, ha 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 ha, just kidding. And, no, I'm not kidding. They're derived from, again, the first two equations that we saw, okay? Now, you might be wondering, oh my god, there are 4 equations. Which one do I use and when? We will talk about that when we talk about the problem solving, but notice that I want you to notice something, and each of these equations, they feature a subset of the SUVAT symbols. So there are good times to use this one and versus this one, for example, because for example, this last equation here, you might not have time. You might not be given time for you to calculate anything, but you might have the other symbols in this equation, 2 variables to help you calculate the missing one, okay? So which equation you use really depends on what you have and what you want to find out. If you are missing one of the variables, there might be that will close your doors to some of the equations that we have here, okay? So this concludes me kind of briefly going over what the 4 equations are. And again, you're really, to get better at it, to know these well enough, it's better to practice, okay? You might be asking, oh, Miss, do I need to memorize all these equations? For me, you do not need to memorize these equations because they are in your data booklet. You'll be given a data booklet, but you are expected to know how to use these equations well. And maybe, if you do enough problems, you would already have memorized these equations off the top of your head because you use them so many times, okay? I find it useful to memorize them because I can freely manipulate, or I can freely think through a problem and piece it together for myself. But of course, that takes time and practice, which I believe you can achieve as well. It takes patience and time, but it's not undoable. Now comes the time where I will derive the last 2 equations, and I suggest that if you don't want to listen to me yabber for a good amount of time, I recommend either pausing the video and just skipping to the end, or you can fast forward through derivations, mute me or something, so you get an idea of what's going on, okay? So here I go! So how do I put these two together? Notice one thing in this equation is that it does not have final velocity, okay? And so what I want to do is I want to substitute one equation with final velocity into the other one. And then we will have to rearrange it to get our final answer here. So I have S, okay? And then my final velocity is substituted with this guy over here. So I'm going to put that in red. U plus AT plus U again. And all of these are in brackets times the time divided by 2. And now after I combine a few things, like this U and that U can be combined together to give me 2U plus AT over 2, all of that over 2, and then all of that multiplied by the time. What I'm going to do is I'm going to multiply the time in, I'm running out of space, okay? So that gives me 2U times the time plus A, and if I take time and times time again, that gives me time squared. All of this divided by 2. Next step is dividing everything by the two terms by 2, so I get S. 2 divides these guys, so I get 2 UT divided by 2. Hopefully you'll get to UT one day. Plus, oopsies. Plus, and ATO divided by 2. And here's where things start to happen. And that is the 2 here cancels out. And really, what I can write this here instead is, instead of AT squared divided by 2, I can do 1/2 times the AT squared. It means exactly the same thing. So I get S is equal to UT, going to university one day, plus 1/2 AT squared. Okay, so that's our first equation. Notice it's the combination of the two equations. Next one, we have V squared, like V squared, U squared plus 2 S's. Let's combine these two equations together, and notice again the time is missing. So what you could do is substitute time from one equation into the other. So I'm just going to substitute in t. There are other ways to do it just as effective, but I guess you're used to it, so I will do what you are used to, so it will make more sense. So what I'm going to do is I'm going to isolate t from this equation, and I'm going to substitute it in here. So let's do that. I'm going to write v equals to u plus at, and to get that t to the one side, I need to first move the u away first. You might be wondering, why am I moving the u away and not the a? So remember, you gotta, I like to think of solving for something side of the equation as peeling an orange. You gotta peel the outer layers before you peel the inner layers. So we gotta peel what's outside of this term. Notice TA is one term. I gotta peel the other terms away before I get to the coefficients of t. So now we're left with AT. Now I can peel the inside of the orange by dividing both sides by the a. Don't forget to divide everything on the other side of the equation by a, leaving me with t is equal to v minus u, giving over all over a. So let's substitute this in here, okay, in this other equation here. Maybe I'll use red for that matter, okay? So let's use this as red. I get, as a result, now this side of the equation, I get S is equal to V plus U times the time, and that's where I substitute everything, V minus U divided by A. And what I'm gonna also do here is I'm going to put a few things, separate a few things out, so it's a little bit easier on the eyes. So here I can put the I can put the 2 here at the bottom, and I can write it like that. That's fine, okay? It's just one side of the equation multiplied by the other side, okay? And to make things a little bit clearer, what I'm also going to do is, using a different colored pen, is I'm going to bring the 2a to the other side. Since they're both on the bottom, I need to multiply them. Otherwise, how are we going to get 2 s's? Right? So let's do, okay, so I get 2as equals to v plus u, all of it multiplied by v minus u. And now you're thinking, huh? How do I get this end of the equation? So something cool that does happen is after you FOIL this, if you have seen it or heard it in math, is remember when you multiply this, it's this times this, and then this times that, this times this, and this times that. Outside multiply, and then the insides and everything. And then you add up the total, which what it is what it is. But the cool thing about this one is you have the difference of squares. And whenever you get 2 things added together, multiply 2 things subtracted, you always get the difference of 2 squares. So first we have the v squared minus u squared. It's just a cool mathematical thing that happens. If you are not sure how it happens, I'm sure you can look that one up. And of course, we're not a math class. I'm just showing you what happens when you derive this. Now we end up with something very close to what we have in the end. And if you want to, if you don't believe me, you just move this one to the other side to make it look exactly like the equation that we have over here by adding this, my bad. By adding the u squared on both sides to move it to the other side, giving you finally u squared plus 2 s's gives us v squared. V squared, okay? Phew! Good job, everyone. You've made it. Okay, so that's the first part of your big kinematics lesson series. I know you're thinking, oh, stop making these long lesson series. It's too much. But hopefully you have gotten something from this video, or at least it was, hopefully it's a starting point for the rest of the lesson series, okay? Please, 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 please practice, 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 practice. The upcoming videos will feature more examples than my current video, okay? Next video, part 2, I will talk about problem-solving skills using kinematics equations. That's where I will go over how you might select which kinematics equations to use, okay? So please, please stay tuned for the next one. It's an important one. I think it's necessary for you to watch. Otherwise, great job for getting through that first video. And I am with you. It's a long ride. We can do it. And afterwards, it's going to help you a lot in the long run, okay? You did a fantastic job. Good luck, and I will see you back for part 3.